Hello, in this video I'm going to talk about the idea of limits. Now, when we talk about the idea of limits, we look at a function, which in this case is the position function s of t, equal to negative 16t squared plus 128t plus 144. Now, 128 is the initial velocity of our function, and then 144 is the initial height. Now this position function actually is related to a projectile being propelled upward, and then from there you have that over time that it will be in the air, and then eventually it will hit the ground. From this case, it's from a height of 144 feet. Now what we want to look at to kind of get the idea of a limit is to first look at what we call the average velocity. Now, when we talk about the average velocity is given by s of b minus s of a divided by b minus a. Now what that means is that all that we're finding in this computation is like what was the average rate of change during this time interval, which in this case we're told that we want to find the average velocity from 1 to 4 and then 1 to 2. So to do this problem, we would first have to figure out what s of 1 is. So let's say that we want to find the average velocity for s of 1. So let's do it like this, because I noticed that basically this kind of looks like a slope. So I'm just going to call this the average. Now, so we're saying that we want to find s of 4 minus s of 1 divided by 4 minus 1. Okay, so what we'll need to do first is to figure out like what is s of 4. Now, s of 4 and s of 1. Okay, so s of 4 is equal to negative 16 times 4 squared plus 128t, not t, but 4, right? Okay, so plus 144. Now, when you simplify this, you're going to get 400. And then similarly, if you plug in 1 into your equation, you're going to get that that's going to be 256. Okay, so we have that this is going to be 400 minus 256 divided by 4 minus 1. But when you do this computation, this is going to give you 80. Okay, so hang on. 144, sorry. So 144, I'm thinking of the next problem, divided by 3. Okay, so what this does is it gives us that this is going to be equal to 48. Now, because I'm finding the average velocity and the position function s is in feet, and then you have that t is in seconds. So what this means is that the average velocity would be 48 feet per second. So we have that the average rate of change is 48 feet per second. Now, I kind of want to do the same thing, but with the other time interval. So I have that I want to find the average velocity at s of 2 minus s of 1, all divided by 2 minus 1. Now, I need to find s of 2. Well, that's going to be negative 16 times 2 squared plus 128 multiplied by 2 plus 144. Now, this equals 2, so when you plug in 2, you get 336. So that's going to be 336 minus 256, all divided by 2 minus 1. Now, what this does is it gives you the following. It gives you 144 over 3. Okay, but if you simplify that, 144 divided by 3, I think I might be looking at the wrong one again. Okay, sorry. So this is going to be, let me just change that. I got my notes backwards. So, yeah, that should be just 80. Okay, so it's going to be 80 divided by 1, and that's just going to be 80. So that's 80 feet per second. Now, one way that we can look at this is that you were finding the average rate of change over that specific time interval. So what you're also finding is what we call the secant slope. So to kind of give you an idea, like what we just did, imagine if you go ahead and you draw the graph of the equation. If you draw the graph of the equation, this is something, what it'll look like. So we have that that's going to be 144. But then, you know, like if you choose 1, like maybe that's 1 right there. But then you just choose another point, like right here. This right here, that joins these 2 points, that's the secant slope. So like, you know, if you say that, for example, that that's t, and let's just move this over. So like if you say that that's t, then that means that we can find essentially just like the change in t, and then we can find the change in s. So what that means is that basically you have that the slope is equal to the change in s over the change in t, which essentially this is just going to give you that you have s of t minus s of 1 divided by t minus 1. So what this is the secant, because you have that you're just joining it by these 2 points right here. So we have that that's going to be what we call the secant, but that's the same thing if we call it the average rate of change. So we have s of t minus s of 1, and that's all divided by t minus 1. But I have that if I was to, let's say, take the limit as t approaches 1, well, in this case, what you have is that you're taking the limit of the secant slope, and eventually what's going to happen is that you're going to get a line that runs tangent to that point at 1. So you have that this is going to be equal to the limit as t approaches 1 of, okay, so in this case you have, let's see, yeah, so in this case you have that that's going to be s of t minus s of 1, and all of this is divided by t minus 1. But what this equals to, once you get t close enough to 1, so if you kind of look at this, like the change in s over the change in t, most people can say, okay, well that's distance over time, which is velocity. So in that case, you have that this is going to give you the slope of the tangent, but that's also known as the, well, we're going to say instantaneous velocity. So that gives us the instantaneous velocity. Now, interestingly enough, okay, so we figured out that the average rate of change was 80 feet per second when we got to close to 1. And of course, it was 48 feet per second for from 4 to 1. Now, suppose that we want to kind of continue this whole idea where we want to find the instantaneous velocity at t equals to 1. So what that means is that all that we need to do essentially is just to go ahead and plug in different values, for instance, because like notice that if we go ahead and we write the limit as t approaches 1 for s of t minus s of 1 all divided by t minus 1. Now, I would be naturally inclined to say, well, why don't you just plug in 1 into the t value and then just be done with it? But there's an issue right there. You get 0 over 0, which is indeterminate. So what we can do is just go ahead and say, okay, well, this is the limit as t approaches 1 of s of t is going to be negative 16t squared plus 128 t plus 144 minus 256 all over t minus 1. Now, this simplifies to the limit as t approaches 1 of, okay, so that simplifies 144 minus 256, that's negative 112. So I have, that's going to be negative 16t squared plus 128 t, and that's going to be negative 112 all divided by t minus 1. Now, if I was to basically just ask, for example, and notice that even if you plug in 1, it's still gonna give you 0. 0 over 0. Now, if I wanted to look at smaller time intervals, then I can do that. For instance, if we look at smaller and smaller subintervals, and you can kind of see like what it's gonna go to. For instance, so like if I was to look at, for example, like if I wanted to look at the time interval from 1 to 1.5, then in this case you could find the average velocity until you get close enough to 1 by making this point smaller and smaller and smaller. So for instance, if you did do that, well, the only thing that you would need to do is just really substitute the 1.5 into this equation. So let's say that we do that. So let's say that we go back, or we go to our calculator and we say, well, negative 16 multiplied by 1.5 squared plus 128 times 1.5 minus 112. And then we divide this by 1.5 minus 1. And that gives us 88 miles, I'm sorry, 88 feet per second. I'm thinking of another thing. So this gives us that, yeah, if we find the average rate of change, so this is the secant, this equals to 88 feet per second. Now, if I do that repeatedly, where I just find my different time intervals, like for example, like 1 comma 1.1, well, you're going to do that same computation where you basically just plug that back into this secant slope. Um, so that'll be, okay, so how about we do like, all as one. Like, okay, let's just do it like this. Um, Negative 16 times 1.1 squared plus 128 times 1.1 minus 112, and then we have 1.1 minus, let's see, minus 1, right? Okay. So we can just hit enter from here. So let's see, 90, whoa, okay, so it jumped up, but that's because I incremented by like 4/10. So it jumped up to 94.4. So we have that, for this one, we have that that's going to be 94.4, and what is that? Feet per second. Okay, so I can repeat this process, for instance, by looking at 1 comma 1.01, and then I can repeat this process by looking at 1 comma 1.001, and then I can look at a closer value like 1 comma 1.0001. Okay, so take like a moment to find the average rate of change from these time intervals and see like what you get. You can kind of tell that it's increasing in any case. So if you go ahead and you find the remaining, and hopefully you did pause, so we have that this is 95.84, and that's feet per second. Then we have that the next one is 95.984 feet per second. And then we have that the last one is going to be 95.9984. Now, hopefully you can kind of tell that there is a bit of a pattern in what it's approaching. So once again, kind of take a moment to say, well, I can probably conjecture that the limit as t approaches 1 for s of t minus s of 1 divided by t minus 1, that this is equal to 96 feet per second. Now, in a way, you don't really have to do it this way because, for instance, all that we really needed to do was just plug in values that were close enough to 1. So like, that could be like 1.1, 1.01, 1.001, 1.0001, but then you also have to try from the left side, like 0.9, 0.99, 0.999, and so on. And eventually you'll see that it equals to 96 feet per second. Now, that may take forever though when you do it like that. So one thing that you should notice is that when you look at so we've kind of guessed based on the calculations that it's going to be just 96 feet per second. But if you go ahead and you look at the secant slope, or the average rate of change that you were working with, you have that that's going to be negative 16 t squared plus 128 t minus 112. All of this is divided by t minus 1. So you're going to learn that whenever the limit expression gives you like a 0 over 0, the indeterminate form, you're going to learn that basically the way to solve those is to just factor. So this means that I can just factor this as negative 16 multiplied by, let's see, um, well, what I want to do is go ahead and just factor this by taking out the negative 16, so I have t squared minus 8t plus 7, and then this is divided by t minus 1. Now, this equals to, we're just going to say t approaches 1, and we're going to factor this even further. So we have negative 16 times t minus 1 multiplied by t minus 7 divided by t minus 1. So what this does is it tells us that the t minus 1 factor cancels out entirely. So we have that that's going to be where we cancel this out and cancel that out. Now this is kind of nice because it tells us that we have the limit as t approaches 1, and I have negative 16 times t minus 1. Now note that this is the average rate of change. That's a 7. So notice that if you plug in the 1, you get minus 6. So you get negative 16 times negative 6, which, what does this equal? Well, 96 feet per second. So we have that taking the average rate of change and taking t to 1 actually does help a little bit. Now, what we're going to learn moving forward into the course is that you can actually figure out, you know, like what an equation of a line would happen to be when you use 96 feet per second, for instance, because take a look at the graph of the equation. Like, okay, so I graphed it in my I graphed it in the in Desmos.com, and this is the equation that I have. So notice this. It was thrown from an initial height of 144 feet, and this is the model of the heights. So we have that it reached a highest height of 400 feet, and that's after 4 seconds. But then it hit the ground after 9 seconds. But look at this. The line right here represents what we call the tangent line. And, you know, we'll learn, like, for example, like, how do you find this tangent line? And right here, at this point, this is exactly the point where we have that we were looking at the average rate of change, and then we looked at the instantaneous velocity. Right now, we actually don't know, like just looking at the graph, I mean, we can't really tell, like, you know, what rate this is increasing by, but we already know that it's 96 feet per second, meaning that the slope of this line is 96 feet per second. But to be to give you kind of like a more of a preview on like what is the point of the tangent line, the point of the tangent line is not only finding, you know, things like the instantaneous rate of change, but also trying to estimate values along this curve. So for instance, if I wanted to know 1.0001, I can actually use this line to see, you know, like if I use a very close value to estimate what that is. So like, you know, 1.1 is approximately 266. 1.07 is approximately 26.72. But notice that as I go along the tangent line, that the gap between the two curves, it gets bigger and bigger, meaning that I can't use faraway values to estimate, because it's not going to be a good estimate in that case. Furthermore, see like how the line is positive, meaning that if I tried another value on this side, it would actually be decreasing. Why? Because it's slowing down. But then, like if I look at, say for example, at the maximum, well, we just said that the positive slope would be on this side, the negative slope would be here, but what happens right here? Well, if we graph this line, well, now we have a horizontal line. If that line is horizontal, that implies that the slope is 0. So in that case, that means that if we have a slope of 0, that means that that's where the function becomes constant, but it also implies not only that, but it implies like a maximum or a minimum in this sense. So notice that like this is the maximum. So if we know where the instantaneous rate of change, or maybe let's say like this, if we know where the velocity is equal to 0, that's where it just stopped. So we could probably set up an equation where we set the velocity equal to 0, and then we just solve from there, and in this case it gives us 4. From there it's just backtracking and plugging 4 back into this equation and then simplifying, and then from there we'll get that the maximum of height is 400. Okay, so that's going to be the idea of a limit for how we look at you know, equations and their average rates of change, or their instantaneous rate of change, or the instantaneous velocity. You know, we can say it like that instead. Now, one thing though that we could have done instead is we could have set up our equation as follows. Since I had that t was moving in increments, like very close to 1, I can think of it like this. What if I was to say from 1 to 1 plus h? Well, in this case, like I said, h, or the 1, you had that you were just getting closer and closer. So you could say h is approaching 0, and then just use s of t plus h minus s of t divided by h, because essentially the change in t is h and the change in s is s of t plus h minus s of t. The only difference is that you need to put a 1 right here, and you need to put a 1 right there also. So I would say, like, you know, yeah, this reduces down to, or it becomes the limit as h approaches 0 of s of 1 plus h minus s of 1 divided by h. Now, if you work out the math to this, you will get the same exact thing. You'll get 96 feet per second. Now, if you wanted to find the tangent line, you have that this is the slope that passes through 1. So in this case, you would just say y minus 256 equals to 96 multiplied by, not t, I'm sorry, um, not, well, we can use x, okay, so we'll just use x. Yeah, just go back to the equation of the line in desmos.com if you want, or just change this to a t in either case. Okay, so this will be x minus 1. Now this represents the tangent line for what passes through 1. So this is the tangent line. And notice that I use the point slope formula for finding the tangent line. But you can also use, you know, like those others, such as like y equals mx plus b. Okay, so, or we'll just put it again, y minus y1 equals to m times x minus x1. Okay, so that's going to be it, and this should give you enough in terms of like the idea of taking a limit.